Hello everyone, and welcome to our breakout session, Scaling Responsible MLOps with Azure Machine Learning. My name is Daniel Moth, and I lead the team of amazing PMs working on Azure Machine Learning. If you're joining us from the AI into Focus session, in this talk we'll go deeper into Azure Machine Learning, including responsible AI and MLOps. We'll show you the code and tools used to build what you saw there. If instead your build journey starts here with us, no worries at all. We will not assume that you have watched any other talk. But I do recommend that you watch later the AI into Focus recording to learn about the AI announcements that go beyond Azure Machine Learning. In fact, let's put Azure Machine Learning in context with the rest of the AI stack. With the Azure AI stack, you have the flexibility to start as high as you can with pre-built AI applications and go as low as you need for maximum customization. At the top, with Applied AI Services, you can use specific applications, including Bot Service for conversational AI and Form Recognizer for recognizing and extracting intelligence from specific document types. Below that are Azure Cognitive Services, which are domain-specific pre-trained models spanning vision, speech, language, and decision-making. Cognitive Services are built on the foundation of Azure Machine Learning. As a user of Cognitive Services, you don't need to know that. But if you do want access to that foundational layer, you can get that by using Azure Machine Learning directly. Azure Machine Learning is a managed end-to-end machine learning platform for building, training, deploying, and operating machine learning models responsibly and securely at scale. Those models can then be accessed by any application that wants to benefit from them. Let's dive deeper into Azure Machine Learning, or the shorter name that I like to use, Azure ML. I'm excited to talk to you about Azure ML, and what excites me even more is learning how customers are benefiting from Azure ML. One customer example is Kantar Group, who work with some of the biggest media companies in the world to improve brand awareness. They wanted to help their clients anticipate customer behavior and understand customer propensity for churn. They turned to Azure ML, including the automated ML capabilities, to analyze behavioral data and profile customers. Azure ML's integration with cloud storage capabilities and with analytics services enabled the data scientists to automate simple tasks and allowed its engineers to focus on the company's most complex workflows. Although they had tried out other machine learning platforms from various other companies, Kantar wanted everything: data storage, data cleaning, machine learning and insights, and visualization all within a single solution. And Microsoft was, of course, able to provide exactly that. Azure ML provides an end-to-end machine learning platform for managing all the phases of the machine learning lifecycle. Before we dive into Azure ML itself, let me share how we view the machine learning lifecycle based on widely accepted best practices, but also on the learnings from our internal and external customers doing this in the real world. Before creating a machine learning model, the data must be prepared. Machine learning projects often use massive, diverse data sources. The objective of this phase is to transform raw data into a clean dataset that can be used for building models. Next, the data is used to start building models, identifying the parameters, features, and choosing algorithms that best fit the data. The objective of this phase is to get to a proof of concept, a working model. Think of it as the phase of, it now works on my machine. The next phase is training models. Now, in some situations, building a model and training a model are very much the same phase. The transition is seamless. In other cases, it is a very explicit transition, driven by scale. Either scaling by adding more people, and hence needing better collaboration tools, or scaling by using the full larger dataset and potentially needing more memory, or scaling by needing more compute, whether that means moving from a CPU to a GPU, or to a larger machine, or to several machines. This is the phase that typically benefits the most from moving to the cloud from a local environment. The objective of this phase is to assess the model and end up with the best candidate model possible from the standpoint of performance, accuracy, and whatever other criteria your scenario demands. The next phase is deploying the model, so that it can be invoked from the software that will be asking the model to do its job, for example, to make a prediction. Now, this includes testing in a staging environment with data not previously seen by the model, and potentially A/B testing in production before finally rolling it out. The objective of this phase is to have the machine learning model in production. Next, the model is monitored in production, evaluating metrics and additional performance indicators to diagnose errors and issue warnings. If model drift or data drift is detected as it gets invoked in the real world with new, previously unseen data, retraining may be required, which takes you back to the training phase or sometimes further back to the data collection phase. The objective of this monitoring phase is to alert if the model doesn't behave in production as originally intended. Throughout the lifecycle, you must ensure that you develop an AI responsibly, beginning with properly exploring the data, then assessing the fairness and interpretability of the model you build, and debugging to mitigate any bias that may pollute outputs. Also, you know how nobody does software development today without DevOps practices and processes? Well, in the machine learning lifecycle, successful teams implement DevOps for ML, which is referred to as MLOps. So when choosing a machine learning product, you should ensure it can support your chosen MLOps process, including the roles your specific people perform as part of the MLOps process. Now the question is, where can Azure ML help? Well, Azure ML can support you and your organization at each phase of this journey and throughout the life cycle. If you have stitched together your own machine learning platform and you only want to use Azure ML to replace only one part of the life cycle, you can do that. Azure ML is open and interoperable and composes well with other solutions. Or you can elect to get the full benefit of Azure ML by using it as your end-to-end machine learning platform. You will see aspects of that in the demos we have lined up for you. But at a high level, it starts with data. And Azure ML supports multiple data sources for data preparation, including, but not limited to, Azure Data Lake Storage, Azure SQL Database, and Azure Database for Postgres. Whether you're working with structured or unstructured data, resulting in classical machine learning or deep learning, Azure ML has you covered for building your models on your data. If we skip the middle phases, it ends with machine learning models in production. Models that are being used by either your own custom application or another Microsoft product that you're using, such as Power BI. And those models can be invoked in real time, for example, calling a REST endpoint, or in a more batch processing style, for example, in the context of a SQL query. One point to take away is that Azure ML is not an island. It is well integrated with all the relevant Microsoft products. Now, double-clicking on the Azure ML box to see inside. The way you typically interact with Azure ML is through the Azure ML Studio web user interface. I call it the Studio UI. In the Studio UI, you have options for building and training your model using automated ML, which is a no-code approach, the designer and the built-in drag-and-drop components, which is a partial code approach, or a full code approach with scripts and notebooks. And when you choose the scripts and notebooks approach, you can do that in your favorite editor, if you have one, or you can do it right there in the Azure ML Studio UI. And you can bring whatever library or framework you wish, such as TensorFlow or PyTorch or anything else. Azure ML keeps track of everything so that you know who is doing what and what is getting used and how. So Azure ML facilitates a reproducible process all the way to deployment and monitoring, a process that you can automate and audit. And you can run all that in the cloud, on Azure ML's compute instance, or on Azure ML's compute clusters, or via Azure Kubernetes Service, and also on premises by bringing your own Arc-enabled Kubernetes classes, and you can even do hybrid between Azure, on-prem, and other clouds. Azure ML can help you implement a responsible MLOps process for your entire ML lifecycle, regardless of where your compute is running. Now that we have a high-level understanding of what Azure ML has to offer, let's see it in action. We'll revisit the scenario shown in the AI in Focus session. For those that missed it, we wanted to create a marketing service that takes as input a brief text prompt and generates as output marketing text. And we wanted that marketing service to be backed by a machine learning model. My colleagues Abe and B built that using Azure ML. In addition, we wanted an app that also used machine learning to determine who should be granted access to the service. My colleague Minsu built that. All three folks are here, and they will take turns showing you how that service and app were built. From importing a foundation model to start with, to testing it, to fine-tuning the model, to creating reusable components, to automating the workflow to follow best MLOps practices, to deploying the model, and of course, to using state-of-the-art responsible AI tooling. They will show you everything. Let's start with Abe. He will be using the notebooks experience in Azure ML Studio and look closely at how his code is using the new SDK v2. Abe, over to you.
Thanks, Daniel, for the great intro. Hey everyone, my name is Abe Amargwe, And today I'm going to show you how you can easily load the GPT-2 model into Azure Machine Learning. Test the model locally, and then quickly and securely deploy the model as an endpoint with the GA Managed Inference Service for everybody on the team to use. So let's get started. I will start by finding a transformer model that can help generate content. I really love using transformers, especially with Hugging Face, because the code is so easy. As you can see here, this is all I have to do. For this task, I'm going to build a text-generated marketing service backed by a GPT-2 model that will produce original marketing content. Okay, this looks like a good overview. All right, let's see if I can get this to work in my Azure Machine Learning workspace. All right, we're in the workspace. As you can see, I'm in Notebooks. Here's a bunch of different notebook tools and features here that I could use. Also, I could edit with VS Code if I wanted to, and have access to the Azure Machine Learning Compute instance. I'm going to start by retrieving the Hugging Face model. Notice the first cell downloaded and saved the model to my file directory. As you can see here, there's a model that has been downloaded, so I can see all my model artifacts here. Great. Now I can run the pipeline to test my model locally. The model is loaded. Now let's see if the generator works. Nice. Notice the model is generating some good content. This conference is amazing because the only questions we asked were, what would this book look like? Okay. Let me show you how easy it is to get this model registered in Azure Machine Learning and deploy it as an endpoint. We're going to start by using the brand new Azure Machine Learning SDK v2. I'm going to start by initializing all my variables. We're going to register the model and upload it to the Azure Machine Learning registry. While this is happening, let's see what the registry looks like. In the last cell I ran, I was able to register the model to the Azure ML model registry. I was able to upload the model from a local directory to the Azure Machine Learning model registry, which is a central place for all the models we want to share across the team. This is the model I just registered. Sweet, all my artifacts were uploaded. Now let's go ahead and deploy this model. Now, if you want to deploy this model as an endpoint, we're going to need an environment to run it. Let me show you how to do that. We're going to start by creating an environment. The environment UI in Azure Machine Learning allows you to see all the curated and custom environments you have access to for training and inference in Azure ML. Azure ML also comes with a ton of pre-installed curated environments with the popular frameworks like PyTorch and TensorFlow, as well as custom environments that you created yourself. Now, to create an environment for my deployment. First, I'm going to make an environment called GPT-2 environment test. Now let's select the PyTorch image as the base image, since I know this model is trained using PyTorch. Now let's upload the conda file to make sure all the extra dependencies are added to the environment. The great thing about this view is I can see a preview of the environment files. I see the base image Docker file is already here. Now let me make sure it's named. Now let's go ahead and upload our conda file with all the dependencies. Look, you can see the conda file has all my extra dependencies. I need like ML Flow and Hugging Face. All right, next, let's hit create. Nice. While the environment is being built, let me show you the score script that I'll be using for this model. I want to show you the score script is very similar to the notebook. Look at the way I load the model in the notebook and how I test a prediction. I will show you the scoring script is very similar. We check in the scoring script, and look, we're loading the model the same, as well as we use the same generator as the notebook right here. All right, let's go to deploy this model. Click the model. We're gonna deploy this model as a real-time endpoint. The great part about the environment UI is all in one place. You can create a new endpoint for deployment or use an existing one. You can also select the right environment, the scoring script, and even configure the traffic for your deployment. All right, first, let me use an existing endpoint. I've made this endpoint prior. I'm going to use the same GPT-2 model. I'm going to name the deployment Blue. Let's upload the scoring script I just showed you. And we're going to select the environment we just created. For the compute, we're going to leave it as is. And all right, let me set the traffic at 50/50 just to show you it's possible. And let's hit create. As you can see, I set the traffic to 50/50 and the traffic was split. All right, let's test it. So we're going to test our new endpoint. Let me paste in the prompt. This conference is amazing because, okay, count 3. Awesome. This is great. GPT-2 is working its magic. This conference is awesome because so many people from all walks of life have been involved. I have spent a fair amount of time with my sister, our dad's brother, my parents, and a lot of neighbors trying to figure it out. This is awesome. Thank you, GPT-2. This was so great. I was able to quickly deploy a GPT-2 Hugging Face model from Azure Machine Learning so quickly and easily. Daniel, back to you.
Thanks, Abe. I love how quick and easy it is to deploy a model in Azure ML with managed endpoints. Managed endpoints help you serve, scale, and secure your machine learning models without you having to manage the underlying infrastructure. That's why they're called managed endpoints. And you can do that via the Azure ML Studio UI, or the CLI v2, or the SDK v2. You can also test them locally using containers and even debug them using Visual Studio Code. With managed endpoints, you can perform safe rollout of a model by using native support for blue-green deployment. You can monitor those deployments with built-in integration with Azure Monitor, Azure Log Analytics, and App Insights. Last but not least, managed endpoints provide a seamless experience across both real-time and batch scoring. Real-time inferencing means processing one request at a time, for example, one prediction at a time, whereas batch inferencing would process an entire dataset in one go. We've seen many customers benefit from managed endpoints in their deployments. For example, FedEx Services, who are using Azure ML to model predictions on packages, and Trapeze Group, who are using Azure ML to predict travel time on bus routes in transit systems. Managed endpoints have simplified their AI deployment, reduced technical complexity, and helped them to optimize costs. Besides direct Azure ML customers, managed endpoints are also a great opportunity for independent software vendors to easily integrate with Azure ML. Microsoft partner Seek has done exactly that by integrating Azure ML into their Workbench application that is used by process engineers. Let's go back to Abe to see how he will fine-tune his model based on his own dataset and will do so without leaving the Azure ML Studio UI. Abe, over to you.
I just showed you how easy it is to deploy a pre-trained model from Hugging Face in Azure Machine Learning. In this demo, I'm going to continue using the pre-trained GPT-2 model and fine-tune the model to produce marketing content that sounds like the famous Greek poet Homer. I'm going to show you how I can use the Azure Machine Learning Notebook and Compute Instance to fine-tune this Hugging Face model to produce the right outputs. So in these previous cells, what I've done is some pre-processing to generate raw text outputs of the Homer data. So let's show you what the data looks like. As you can see here, I've already parsed all the data and produced a line to input into my model. Each of these lines come from the home or poems. So let's go ahead and train our model. So we're going to start by importing our model. Before I go ahead, I want to show you, I can see IntelliSense here, and in case I wanted to figure out how to load the model, I can click See Example from GitHub, and I can know how to import the model. Now the model is loaded, let's bring in the variable, and let's test the model. Okay, cool. These predictions are looking good. Looks like we're already producing great content. This conference is amazing because it's a chance to talk about the challenges of the future. However, this is too generic. We need content that sounds like it's from a Greek poet. Let's fine-tune this model. Let's go down to the training part of this notebook. In the previous cells, I did a bunch of pre-processing and tokenizing of the raw data for training. So all I have to do is start training. Let me make sure I have the right compute. Nice. You can see this box is 1 GPU and a bunch of RAM. That'll be more than enough to train this model very quickly. So let's get started. Notice on the right side, this run notification came up. Let's check out what's going on here. Awesome. All my metrics and parameters were automatically tracked here in Azure Machine Learning. The reason that this happened is because Azure Machine Learning is fully integrated with MLflow, which means if you're training an experiment with a library that uses MLflow, like Hugging Face, we will get all the experiment metrics and parameters tracked automatically without adding any Azure-specific code. Let's check out the metrics too. Wow, looks like all my metrics were here without me changing any of my training script. This is awesome. Thank you, Azure Machine Learning. Now let's check if the training results are different from what we originally produced. Now the moment of truth. My model has finished training. Let's see if the results are different. This conference is amazing because it is the first time any Greek has presented. Okay, this definitely is more Greek sounding. You can see the old model is a lot more generic. My job here is done. I have trained and fine-tuned this model. And now I can rest easy. I think Daniel will be very happy. Daniel, back to you.
Thanks, Abe. You saw Abe using AzureML as his workstation in the cloud for interactive development. And there were two parts to that. First, for the purposes of running his code, he was using the compute instance in AzureML, which you can think of as a managed VM in the cloud. And we're continuously making many improvements to compute instance, so if you haven't used it recently, you should check it out. Second, Abe was using the Azure ML Studio UI, which offers the full capabilities of the Azure ML platform. You saw in the Azure ML Studio UI the built-in notebook experience that supports the standard Jupyter Notebook file format, but with a faster and more accessible user interface, which is richer in capabilities like market-leading code completion. Along with that notebook experience, there is also an editor, a file explorer, and a terminal window. Having said that, one of the benefits of Azure ML is that it doesn't lock you in to one style of working. If you wish to code in another editor, such as Jupyter Lab or Visual Studio Code, you absolutely can. The Azure ML SDK and CLI can be used from anywhere to interact with the Azure ML backend. Now, besides coding in whatever editing surface you choose, Azure ML also offers no-code experiences such as automated ML. Azure ML also offers low-code, also known as partial code solutions, such as the Designer, where you can drag and drop built-in components to piece together your ML solution, optionally attaching snippets of code to customize the components for your needs. Now, many of our customers use all of these different approaches, depending on the specific project or the people working on it. One such customer is Scandinavian Airlines, SAS. SAS used Azure ML to build predictive models that improve everyday operations and identify patterns in the company's data, from building models to predict flight occupancy, to forecasting sales, to loyalty fraud prevention. Their developer team leverages multiple model building approaches and tools from Azure ML, from no-code to low-code to full code. Now, we talked a lot about editing code in notebooks. Notebooks are amazing for experimenting, testing ideas out, and building proofs of concept. But as notebooks get larger, and as your team gets serious about operationalizing models to production, that is where you may feel some of the limitations of notebooks. At that point, you may turn to a professional MLOps platform, and mature teams will be looking for the ability to automate their ML solution in a reproducible manner. Just one of the ways that Azure ML supports that is through components. In Azure ML, a component is a versionable, self-contained piece of code. It is analogous to a function. A component performs a step in a pipeline, and it allows you to reuse logic across pipelines. Think of a pipeline as the orchestrator of your machine learning workflow. They can perform tasks such as data processing, model training, deploying into an endpoint, and so on. Now back to our demo. Let's follow B, who's going to start with Abe's notebook and end in a much better place. B, over to you.
Thank you, Daniel. My name is B. Stolnitz, and my job is to take Abe's notebooks and create a production-ready workflow. And of course, I'm going to use Azure ML for that. Let's dive right in. Abe handed me 2 notebooks, which I added to my project. Notebooks are great for experimentation, but Python files will make it easier to refactor his code into components. So I went into each of his notebooks, clicked on Export, and saved the notebooks as files ending with a py extension. Then I analyzed his code carefully and decided to separate it into 4 files. The model notebook turned into the Hugging Face and Register model files, and the train notebook turned into the fine-tune and process files. Let's look at the process file. The purpose of this code is to read the data source and split it into training and validation sets. You can see here that it takes as argument the source folder for the dataset, a train validation split, and the paths where we want to save the training and validation outputs. Notice that I gave it some default values, so if I run it locally, I expect the original data to be under Data Homer, and the validation and training data will be saved under Data Processed. Let's run this code. As you can see, a data process folder is generated as expected and contains the training and validation sets. Now that I have my code nicely refactored into separate Python files, I can create an Azure ML component for each of these files. An Azure ML component it's really just a resource that encapsulates a reusable piece of code with inputs and outputs. I'm going to create resources using YAML files, like this process.yaml file, which, as you can see, contains the arguments that we saw in the code file. I have 2 inputs, a folder with a dataset and a training validation split, and 2 outputs, the paths to the training and validation sets. There's one more thing I need, an Azure ML environment that specifies all the dependencies this code relies on. I already have a YAML file with a configuration for a good training environment, which I named Base-HF Transformer Train. I just need to register it with Azure ML, which I'll do using the CLI with an AZML environment create command. Now let's go to the Azure ML Studio and verify that our environment was created. And it was. Great. Now that I have an environment created in Azure ML, I can add it to the YAML file of each of my components. I could use a CLI command to create these components, but I would need to use 4 commands each time I make any changes to these files, and that would be tedious. Well, I have a better way. I created a GitHub action that watches for changes to Python and YAML files within the components directory and executes the AZML component create command. And the coolest thing about it is that it increases the version number automatically. Let's see this action at work. I'm going to check in the changes to my 4 components. I'm going to make a pull request from my branch to main, merge into main, and the GitHub action kicks in. I'm going to speed up this bit so that we can focus on the interesting parts. And when it's done, we can go to Update Modified Components and see that the GitHub action detected changes to these 4 files and executed AZML component create commands for each file. And we can see here that the fine-tuning component was registered with version 18. Let's confirm that these were created in the Azure ML Studio. Okay, here are the 4 components we created, and the fine-tuning component has version 18 as expected. Remember that one of the inputs expected by the process component is a folder containing the original data. Well, my data is on my local machine, so I need to create a dataset to make it accessible from the cloud. I could use an AZML command for that, but let's use the UI this time. I'll go to Datasets, Create Dataset from Local Files. Let's call it Homer, and choose File for the dataset type. I'm going to click Next, then Browse to find the dataset folder, then click Upload, click Next, and then Create. This creates a new dataset. Let's verify that it contains the files we want. Yep, here they are. Now that I have the dataset and all the components registered in Azure ML, my goal is to connect them into a pipeline that fine-tunes a GPT-2 model with my dataset and registers the resulting model in Azure ML. I could create a pipeline using a YAML file and the CLI, but for this demo, I'm going to create this pipeline using the designer right in the studio. I'm going to select Compute Cluster. I'm going to pick a pretty fast cluster, and I'm going to give the pipeline a better name. You can see here on the left that I can add datasets and components to the pipeline. I'm going to start by dragging the Homer dataset, which I created earlier. Then I'm going to drag the 4 components you've already seen onto the canvas. This one splits the dataset into training and validation sets. This one gets the trained GPT-2 model from Hugging Face, and this one fine-tunes the GPT-2 model, and this one registers the fine-tuned model with Azure ML. We get a little warning in 2 of our components. That's because they expect me to specify some inputs. For this component, I need to say that I want the pre-trained GPT-2 model from Hugging Face. And for this one, I need to specify a name for the output Azure ML model. Now let's connect them. The dataset returns a folder path, which my processor component expects. The processor returns training and validation data, which connect right into the fine-tuning component. The Hugging Face component returns weights, a tokenizer, and a config, which our fine-tuning component expects in that order. And the fine-tuning returns fine-tuned weights, a tokenizer, and a config, which the model registration expects. Now I just need to submit this pipeline. I'll choose the NLP tests experiment and submit. This takes a few minutes to run, so let's fast forward to the completed pipeline. We can now go to Models and see that Model GPT-2 was created. Nice. Let's go back to the designer and click on the fine-tuning component. I'm logging this metric, which tells me that the throughput of this component is 84 training samples per second. This is really good, but I have another fine-tuning component already registered that might do better. Let's try it. I'm going to replace the current component with a new one, reconnect everything, and rerun my pipeline. One thing to notice right away is that my first 2 components are reused. Only the component I replaced and the component that depends on it are rerun. This saves me a ton of time during development. I'm going to skip forward in time once again to the finished pipeline, and I'm going to look at the throughput of this new component. 216 trained samples per second. It's an improvement of more than 150%. How am I getting the speed up? Well, I'm giving you a sneak peek of something Microsoft has been working on, which is still in private preview. It's a new Docker container that brings together a collection of tech that accelerates deep learning training. Okay, that wraps up my demo of Azure ML components and pipelines. Now that I have a pipeline that registers my fine-tuned model with Azure ML, I'm going to show you how to deploy that model at scale with a managed endpoint. Let's look at the code. The first step in deploying a model is to write a score.py file, like the one I'm showing here, that takes in some user input and generates a prediction using the trained model. This file needs to have an init function that AzureML calls when the endpoint is first created, and a run function that AzureML calls each time the endpoint is invoked. The code is ready, and now I want to create an AzureML endpoint so I can deploy this code at scale in the cloud. An endpoint can have multiple deployments. For example, if you want to do A/B testing, you could have some of the traffic go to one deployment and the rest to another. But we're going to keep it simple in this demo and create a single deployment that takes all the traffic. Once again, you have many options to create AzureML resources. You could use an AZML command in the terminal or the Azure ML Studio UI. But this time, I'm going to show you how you can use the VS Code extension for Azure ML. I'll go to the Azure icon on the left taskbar and click on the plus sign to create an endpoint and select Managed Online Endpoint so that Azure manages the compute resources. I'm going to call it Homer Endpoint. And you can give it tags, but I'm going to delete them to focus on the essentials. I'll save this as endpoint.yaml. Great. Next, I need to create a YAML file that configures a deployment within the endpoint. I'm going to click on this plus sign and choose Managed Online Deployment. I'm going to specify the model that we tuned earlier using a pipeline and the location of the score.py file that I just showed you. I'll give it an inference environment that I already registered, a machine type, a name, and the name of the endpoint that we chose in the previous YAML file. I'll remove the scale settings for now. We'll be talking about scaling later. I'm going to add one more setting. I can press Control Space to see all properties available to me. Then I'll start typing. And here's the property I'm looking for, instance count. I'll set it to 2 so the deployment can handle more traffic. I'll save this file as deployment.yaml. I'll go back to my endpoint file and create the AzureML resource by right-clicking and selecting AzureML Execute YAML. If you look in the terminal window, you can see that the VS Code extension automatically runs the write AZML command to create the endpoint. Awesome. Now I'll do the same for the deployment. I'll right-click, select Execute YAML, and the command is executed. This takes a few minutes, so I'm going to fast forward. And okay, the deployment is created. Let's go to the Azure ML Studio. You can see that our endpoint is here, and if we click on it, you can see that it has a deployment called Blue. We want this deployment to handle 100% of the traffic for this endpoint, so let's update the traffic to 100%. And we're ready to test the endpoint. We'll go to the test section and type a prompt. This conference is super awesome because I click the test button to see how Homer would have completed the sentence, and we get our result. This conference is super awesome because it is so much more than just a meeting of delegates, the people and their thoughts on pressing issues of our day and age. So true, right? To make sure it can handle a lot of traffic, I can change the auto-scaling settings. Let's click here, choose Custom Autoscale, then Scale based on a metric, and add a rule. Here's the rule I want. When CPU utilization is larger than 70%, I want to increase the instance count by 1. I'll add this rule, which shows up here, and I can save it. My endpoint is fully set up now and ready to be used in production. Let's look at the Consume tab to see how we can invoke it. Here you can see the HTTPS address and the key you need to access it. You can now invoke it by doing a simple post request from your app's code. I'm going to show you how I can invoke it using a curl post command in the terminal. here's the prompt input I'm going to pass to the endpoint. And now I can execute a curl in the command line using the HTTPS address and key you saw in the Azure ML Studio and the JSON file with the prompt. And here's the result. Very cool, it worked. In the last couple of demos, I showed you the entire process for turning your data science notebooks into production-ready code. I refactored the notebooks into components, connected them into a pipeline that creates an Azure ML model, and deployed that model using an online managed endpoint. Thank you, and back to you, Daniel.
Thanks, B. That covered a lot of ground. I want to underline a few of the things shown. First, you saw in that last demo the new CLI v2, whereas earlier Abe was using the new simplified SDK v2 to achieve some of the same outcomes. I love how the new CLI v2 now exposes the full power of Azure ML via intuitive commands combined with self-descriptive YAML files. With v2, anything you can do with the Studio UI or the Python SDK, you can also do with a language-agnostic CLI. A primary use case for the CLI is management of Azure ML resources, like workspaces, compute, data source, and also management of assets, like data, models, and environments. The second thing I want to underline in that demo is that you saw components and pipelines in action. They are the building blocks for operationalizing models, and they are foundational to an MLOps platform. I will let you in on a little secret. As you would expect, Azure ML is the standard platform for other Microsoft product teams to use for their machine learning needs, teams such as Office, Bing, and the largest machine learning workloads in Microsoft. And what many of those teams appreciate the most is Azure ML support for pipelines and components. We have been proving out the capabilities internally, and we're very excited that we can now bring the new capability of custom reusable components to all of you, just like you saw in the demo. Now, experienced folks know that MLOps is the intersection of people, process, and products. You just saw just one example of what a great product looks like for enabling MLOps. Many of our customers pick Azure ML because of its MLOps support, which besides pipelines, includes capabilities such as sharing and collaboration, tracking and lineage that lead to reproducibility, for example, through Azure ML's model registry, by capturing the versioned environment code and data used for training the model. And of course, the rich automation via flexible eventing and monitoring, plus integrations with CI/CD tools. One such customer example is Brazilian-based consumer goods company BRF. BRF adopted Azure ML to develop machine learning models for improving business outcomes and sales forecasts. They use the MLOps capabilities to automate all phases of the machine learning lifecycle. Because of that, their analysts can focus on more strategic tasks instead of the mechanics of merging spreadsheets and running analysis. Now that we've got our model in production, it's time to use it. We want developers to use this service, but first, they must apply to use it. To process their application, we will create an app that will use yet another machine learning model to determine which applicants to approve and which to deny access to the service we just built. In this next demo, we'll see how Minsu is able to use multiple tools in the Responsible AI dashboard to identify bias and debug the model. The dashboard brings together capabilities that help summarize model performance. From the dashboard, we can also export a Responsible AI scorecard so that AI practitioners can get summaries of model performance and insights. The scorecard helps both technical and non-technical audiences understand the impact of applying Responsible AI so that all stakeholders can participate in compliance reviews. Minsu, over to you to show us all that in action.
Thanks, Daniel. Hello, my name is Minsu Thigpen, and I'm a product manager at Microsoft. The model used in the ML app Daniel just mentioned was trained on a historical dataset of programmers who were scored from 0 to 10 based on characteristics such as age, geographical region, what operating system they use, employer, style of coding, and so on. If the model predicts a score of 7 to 10, then they're allowed access. Essentially, this model is allocating opportunity across different developers. So, we should take a closer look at this model to identify what kind of errors it's making, diagnose what is causing those errors, and use those insights to improve the model. After uncovering those evaluation insights on our model, we can then share them via the Responsible AI scorecard with other stakeholders who also want to ensure the app's transparency and robustness and build trust with our end users. With Abe and B, you've seen how they've utilized Azure ML across the Python SDK v2, CLI v2, and the Azure ML Studio UI. The responsible AI dashboard can be generated via a code-first, CLI v2 and SDK v2 experience, or a no-code method via Azure Machine Learning's UI Studio. Let's see how we can create the responsible AI dashboard via the SDK v2 experience. An Azure ML training pipeline job can be configured and executed remotely with a Python notebook. Once you train your model and register it, you can create a responsible AI dashboard by first selecting the components you would like to activate in the dashboard, specifying the input and outputs of each component, and creating a component job for each of them. By default, we use an opaque box mimic explainer for generating explanations. For causal analysis, we're interested in using the historic data to uncover the causal effect of the number of GitHub repos programmers contributed to and years of experience on their score. For counterfactuals, we want to generate 10 counterfactual examples per data point, leading to the prediction value to have the desired score of 7 to 10. For error analysis, we can optionally specify generating a heat map for error distributions across the features of style and employer. Finally, we have a gather component job, which will assemble all our responsible AI insights into the dashboard. We assemble our pipeline job and submit it with a single line. Alternatively, we can create this job with a YAML file to automate creating the responsible AI dashboard in your MLOps via the CLI v2 experience. We can specify all the jobs that we want to kick off: training the model, registering the model, then creating the responsible AI dashboard with a YAML file, and executing the job with a single line from your CLI. Finally, we can create this job without leaving the Azure ML Studio at all, with a no-code wizard experience. If we go to our list of registered models, we first select the model we want to generate the responsible AI insights for. You first pick a train and test dataset that was used to train and test your model. For this scenario, we will be choosing regression. And for the dashboard components we're interested in, we can choose either the debugging profile or real-life interventions profile. We'll move forward and model debugging and customize the dashboard to include error analysis, counterfactual analysis, and model explanation. For error analysis, I can choose up to 2 features to pre-generate an error heat map for. For counterfactual analysis, I'm interested in seeing a diverse set of examples, let's say 10 examples for each data point, where we automatically perturb features just enough so they receive a score of 7 to 10. We can even control which features are being perturbed if we don't want certain features to be changed. This all looks good, and we move on to the final step to configure our experiment. We can name our job that will generate our responsible AI dashboard and either select an existing experiment to kick off the job in or create a new one. We'll create a new one with the necessary resources and hit finish and kick off the job. With that, we can jump into the Azure Machine Learning Studio to see if the job has been successfully completed, and we can see the resulting responsible AI dashboard for our model showing up. Let's go take a look. The responsible AI dashboard is a dynamic and interactive interface to investigate your model and data built on a host of open-source, state-of-the-art technology. We enable an integration of your workspace compute resources to access all the features, such as retraining error trees, recalculating probabilities, and generating insights in real time. The different components of the responsible AI dashboard are designed such that they can easily communicate with each other. You can create cohorts of your data to slice and dice your analysis, and interactively pass cohorts and insights from one component to another for deep dive investigations. You can hide the different components you've generated for the dashboard in a dashboard configuration and add them back by clicking the blue plus icon. We first look at our error tree, which tells us where the distribution of most of our errors lie. It seems that our model has made most of the amount of errors for programmers living in Antarctica who don't program in C, PHP, or Swift, and also don't contribute that often to GitHub repos. We can easily save this as a new cohort to investigate later, but in the meanwhile, it'll show up as a temporary cohort in the subsequent components. Then, looking at our model overview can give us a high-level view of the model prediction distribution to help build intuition for the next steps of model debugging. But let's actually take a look at the Data Explorer to see if feature distribution in our dataset is skewed. This can cause a model to incorrectly predict data points belonging to an underrepresented group or to be optimized along an inappropriate metric. If we bin our x-axis to be the ground truth of different scores a programmer can get, where 7 to 10 is the accepted range, and take a look at the style, we see that there's a highly skewed distribution of programmers who use tabs being scored lower than programmers who use spaces being scored higher. Additionally, since we know our model made the most amount of error for those living in Antarctica, when we investigate location, we see a highly skewed distribution of programmers living in Antarctica who were scored lower. What this means is that our model will unfairly favor those who are using spaces and not living in Antarctica when providing access to the application we built. Coming down to our aggregate feature importance, we can see for our overall model which features were the most important to the model's prediction, and we can see the style, tabs and spaces, is by far the most considered, then operating system, then programming language, and so on. If we click into style, we can see that using spaces has a positive feature importance and tabs has a negative feature importance, showing us that spaces is what contributes to a higher score. We can also look at two specific programmers who got a low and high score. Row 35 has a high score and uses spaces, and row 2 has a low score and uses tabs. When we look at the individual feature importances of each programmer's features, we can see that spaces positively contributed to row 35's high score, while tabs contributed negatively towards the lower score of row 2. We can take a deeper look with counterfactual what-if examples below. When selecting someone below the 7 to 10 desired range prediction, we can see what bare minimum changes could happen to their features to lead to much higher predictions. In this programmer's case, some recommended changes would be switching their styles to spaces. Finally, if we wanted to purely use historic data to identify the features that have the most direct effect on our outcome of interest, in this case being the score, we can use causal analysis. In our case, we want to understand the causal effect of years of experience and number of GitHub repos a programmer has contributed to on the score. The aggregate causal effects show you overall for your whole dataset, on average, increasing the number of GitHub repos by 1 increases the score by 0.097, whereas increasing the number of years of experience by 1 doesn't increase the score by much at all. However, if we want to look at an individual programmer and perturb those values and see the outcome of specific treatments to, let's say, years of experience, we can see that for some programmers, increasing the years of experience does cause the score to increase by a bit. Additionally, the treatment policy tab can help us decide what overall treatment policy to take to maximize real-world impact on our score. We can see the best future interventions to apply to certain segmentations of our programmer population to see the biggest boost in the scores overall. And if you can only focus on 10 programmers to reach out to, you can see a ranked list of top K programmers who would gain the most from either increasing or decreasing the number of GitHub repos. Besides this dashboard, which is designed for data scientists to explore and evaluate model insights and inform their data-driven decisions, we also enable a scorecard you can easily configure, download, and share with your technical and non-technical stakeholders to educate them about the model and build trust. This scorecard could also be used in compliance and audit reviews to inform the stakeholders about the characteristics of your model. We can find these where we find the Responsible AI dashboard. Let's look at the one generated for the model we just looked at. The configuration stage requires you to use your domain expertise around the problem to set your desired target values on model performance and fairness metrics. First, we want to show you the characteristics of your data, as any model story is incomplete without the right understanding of your data. We also have the model performance summaries explaining your model's most important metrics and characteristics of your predictions and how well they are satisfying your desired target values. Scrolling down, you can even see the top performing and worst performing data cohorts and subgroups that we readily extract for you to see the blind spots of your model. Next, we show you your top most important factors impacting the model predictions, a must-have to build trust with how your model is performing its task. Finally, we show you your model fairness insights and how well your model is satisfying the fairness target values you had set for your desired sensitive groups. Now that we've walked through analyzing our models using the Responsible AI dashboard and scorecard, we are more empowered to develop our machine learning models responsibly. Daniel, back to you.
Thanks, Minsu. I'm excited to share that the Responsible AI dashboard and scorecard are ready to use in public preview. These tools are helpful, if not essential, in regulated industries and for scenarios with sensitive data. As one example, when financial organizations use machine learning to approve or deny a loan, how can they know it was done for the right reasons? Professional services firm Ernst & Young make fairer loan decisions faster by using Azure ML and some of the tools you saw in the demo to assess and mitigate unfairness in machine learning models. That helps their customers and the regulators develop confidence in the decisions that the AI system recommends. As another example, the UK National Health Service used the Responsible AI dashboard to build a model that predicts risk levels for patients undergoing hip or knee surgery. That enables the NHS to clear the queue efficiently and provide the best treatment to their patients. Even if you're not in a regulated industry yet, and even if you're not working with sensitive data, you should be excited about these kinds of tools which help you create higher quality models in general. When we compare traditional software development with using machine learning models, it is like having an algorithm produce results, but you cannot see or debug the algorithm's code. Models are opaque. So being able to use this kind of tooling to explain what a model does is critical to robustness and accuracy. Now that wraps up the demos for today. At the start of the talk, I mentioned Azure ML support for on-premises and hybrid scenarios via Arc, where you can bring your own Arc-enabled Kubernetes clusters. You then saw in action managed endpoints, the SDK v2, the CLI v2, support for custom reusable components in pipelines, and the Responsible AI dashboard and scorecard. We mentioned, but didn't show, automated machine learning, or automated ML for short. We continue to invest heavily here. After you provide automated ML with a dataset, it automates the feature engineering, algorithm selection, and hyperparameter tuning to find the best model for your data. Many of our customers have been enjoying automated ML with structured data, for example for forecasting scenarios, and now we're announcing support for unstructured data, such as vision and language, for example for sentiment analysis. Now what excites me the most about automated ML is the new ability of code generation. Initially, we expected automated ML to be used only by folks who didn't have the skills to code a solution. However, many of you who can code told us that you use automated ML because it produces great models, and in many cases, there is no need to handcraft a solution. What we heard was that you would still want to get the code, either due to policy in the organization, or so that you can take the code and try to improve the model even further. In other words, automated ML can be an accelerator to getting started, zipping through the proof of concept phase. Everyone can start with automated ML, and if you want to explore the code to learn from it or to improve it further, generate the code and continue from there. Lastly, we showed a lot of Python, but Azure ML is language agnostic and supports R as well, and the new CLI v2 improves that further. Additionally, we're announcing integration with RStudio Workbench. You can easily set up RStudio Workbench on your Azure ML Compute instance and plug in your RStudio license to use the RStudio IDE from within Azure ML. Now, there are many other improvements we don't have time to cover, such as, in addition to getting visual notifications in the Azure ML Studio for interesting events, you can easily configure additional email notifications, for example, when a long-running training job completes or fails. Enhanced data labeling with text named entry recognition, NER. Tagging support for cost management and reporting. Finer-grained access control for data in a workspace. And I could go on, but I'll stop there. You now know that by using Azure ML, you can improve your time to value with integrated tools. You can operationalize at scale with MLOps to deliver responsible solutions. And you can rest assured you're doing that development on a secure, hybrid, and compliant platform. If you have any questions on how to use Azure ML, you can connect with our team of subject matter experts by signing up for one-on-one consultations available here at Build. In addition to the AI into Focus session that I recommended earlier, I highly recommend you check out our other breakout session on cognitive services. On behalf of the entire Azure Machine Learning team, thank you so much for staying with us to the end. Until next time, take care.